The masses of four vehicles and the net forces acting on them as they enter a highway are reported in the table below. So here we've got four different types of vehicles, different masses, same amount of force applied. So which vehicle has the greatest acceleration as it enters the highway? So we're looking for acceleration. So we have acceleration equals force divided by the mass. We've got the first one, 4,500, divided by 1,500 is 3 newtons. The next one, 4,500 divided by 1,200 is 3.75 newtons. 4,500 divided by 1,800 is 2.5 newtons. And the last 4,500 divided by 2,000 is 2.25. We're looking for the greatest acceleration as it enters the highway. That's going to be this one right here, the coupe, because it is the largest one. And truly, guys, we wouldn't even have to do that if we knew that same force, we're going to go for the smallest mass. But to prove ourselves correct, we've got the calculations there. Number 12, the list includes 6 stations. We've got a book sliding across the table at a constant speed. We're looking for unbalanced forces. So constant speed, that's going to be balanced. A ball sitting on a shelf, it is balanced because there is no movement. A can rolling down a ramp, unbalanced because as things roll down, they get faster and faster. That's a change in speed. A swing moving back and forth, that's a change in direction and speed, so unbalanced. A car traveling at a constant speed, it's moving at a constant speed, so there's no change, so that is considered balanced. And a bird landing on a branch, well, first it was moving and then it landed, so it stopped, so that is going to be a change in speed. We're looking for things that experience an unbalanced force. That's going to be the can, the swing, and the bird. Your correct answer is H.
All right, number 13. NASA's Space Shuttle program was active from 1981 until 2011. The photograph shows rockets carrying a space shuttle off the launch pad. How can Newton's law of action-reaction best be applied to explain the movement of the rocket? Well, we know that Newton's law of action-reaction states that for every action, if this is the action, there is an equal and opposite reaction. Okay, so we know that as the rocket, the fuel goes out of the ship, it's going to push down on the Earth. The Earth then is going to move the rocket forward by pushing in equal and opposite directions. So let's see which one of these best fits Newton's third law of action-reaction. A, as the fuel burns, gases push against the rocket, moving it upward. Okay, well, gases are pushing for sure. The rocket is moving upward. So far, this one might sound good, but let's double check. As the fuel burns, gases move out of the rocket and reduce air resistance. Gases are never going to reduce air resistance. C, as the fuel burns, the mass of the rocket decreases. The mass does not decrease. The mass is going to stay the same unless you lose half the rocket. And D, as the fuel burns, the rocket moves faster. That doesn't make a lot of sense. The fuel burning is not what moves the rocket faster. That would be an unbalanced force that would do that. So the best answer of these is going to be A. All right, number 14. In a classroom demonstration shown below, the rubber ball is dropped from position 1 as the ball bounces as shown. At which of these positions does the ball have both the greatest kinetic energy and the least potential energy? We know that kinetic energy is energy due to motion or speed of an object. The more speed or motion an object has, the more kinetic energy it has. And potential energy is based on position, or in this case, it would be the height above the ground. So we're looking for where the ball has the most speed and is also the closest to the ground. So obviously at number 1, it's going to have the most potential. That's where it's highest, and it's not moving. Down here at 2, it's going to have the fastest It's going to be moving the fastest speed, and it's also closest to the ground at position 2. Position 3, it has a little bit more potential energy, has gone up, and the kinetic energy has gone down because it's going to stop right there at the top. And then you come down to 4 again. As it's moving up with 4, it's going to be slowing down as it moves up, so it's going to be losing kinetic energy there. The best answer in this case is position 2.
Number 15, the unusual strength of a glue makes it able to hold a heavy object or load as shown in the diagram below. So we've got a diagram. It looks like the load is glued to the fixed board here. If the load exerts a strong downward force, that means that this load is exerting a strong downward force. The glue, what is the glue doing? So does it destroy the force? That doesn't make sense. We're not talking about destroying forces in here. Exert a stronger downward force. Well, if this particular object is at rest, would you agree? If it's at rest, then it is considered balanced. So if it's doing a stronger downward force, then it would be actually moving down, and it is not. So that is incorrect. Does it cause the load to accelerate upward? Is this moving? No. So it's not accelerating upward. Does the glue exert an upward force that is equal to the downward force? Well, that's Newton's third law. That is, for every action, there's an equal and opposite. There's my downward force reaction. Downward force, or upward force and downward force are the equal and opposite reaction. So this is going to be the correct answer. Number 16, the drawing shows two identical airplanes at an air show. The airplanes are flying at the same speed. That's important. Airplane W is flying 50 meters higher than airplane X. Okay, so just looking at this alone, if they're traveling at the same speed, I know we're dealing with energy, so it looks like potential and kinetic energy. So same speed, that would mean the same kinetic energy, because energy has to do with motion. So if they're at the same motion, because they're at the same speed, so they would have the same kinetic energy. However, airplane W is 50 meters higher than airplane X. What we said before is that potential energy is stored energy, and it also has to do with height or position. So the airplane W is flying higher, so this one has more potential energy than airplane X. So let's see, which statement best describes the energy of the two airplanes? Airplane W has a greater kinetic energy? No, they have the same kinetic energy. The two airplanes have the same gravitational potential energy, but different kinetic energies. Again, this one's wrong. They have the same kinetic energy and actually different here, gravitational energy. Airplane X has more gravitational potential energy than airplane W. No, it's actually this airplane W has more gravitational potential energy than airplane X, so that one's wrong. The two airplanes have the same kinetic energy, yep, because they are the same speed, but different gravitational potential energies. And that's yes, so my correct answer is J.
All right, number 17. The picture below shows a baseball bat striking a baseball. Why does the baseball move when the bat strikes it? Here you have the motion of the bat going this way. The ball then flies out and accelerates in that direction. Why does the baseball move? Is it because the contact with the ball releases the bat's potential energy? No, the bat doesn't get its potential energy released by the ball. The guy hitting the bat is the one that, or moving the bat is the one that releases its potential energy. So that's not our answer. Letter B, contact with the bat creates an unbalanced force. Okay, good. We know there's an acceleration up here. So we know their forces are unbalanced. So that may be our answer. Let's hang on to that one, affecting the ball. Letter C, contact with the bat releases the ball's potential energy. Again, the ball's potential energy is not released by the contact of the bat. The only potential energy the ball has is due to its position above the earth. It goes sideways, like this, not downward toward the earth at this point. So that is not our answer. Contact with the ball creates an unbalanced force. Here we have that word again, affecting the bat. So which one of these gets affected, the ball or the bat? Well, who accelerates? It's the ball that accelerates, not the bat. The bat. Okay, number 18. A school bus moves down a road, dropping off students after school. The bus slows down from a speed of 15 meters per second to a full stop over a distance of 55 meters in 11 seconds. What is the average speed of the school bus while the bus is slowing down? Okay, and in this question, the first thing you want to do is figure out what the problem is asking you to find. In this case, it is average speed. And we know that in order to find speed, we can look at our formula chart and learn that it is distance divided by the time. So let's come back up to the problem. We have lots of numbers up here, so let's see if any of these are extra information. A school bus moves down a road dropping off students after school. The bus slows down from a speed of 15 meters. So this to me looks like it is the top speed of the bus, and that's not going to help us find the average speed. That is the top speed. So it is extra information that we don't necessarily need to a full stop. Again, now it's stopped. That's a speed or at rest over a distance of 55 meters. So the total distance the bus took to make that stop was 55 meters, and that's what information we need for our average speed calculation. In 11 seconds, here we have a time. It took 11 seconds to make that 55-meter stop. And 55 divided by 11, we put that in our little calculator, and it equals 5 meters per second squared. We come over to our griddable, and we have our decimal right there. Then our 5 is going to go right in front of the decimal because the decimal in the answer would be right behind the 5.
Okay, number 19. A professional triathlete competes in an Austin bike race. She takes 90 minutes to travel the entire course. Her speed varies from 0 kilometers per hour, that's when she's stopped, while stopped for a tire change, to 30 kilometers per hour while riding downhill. So again, this is her top speed here, and this is when she's obviously at rest. So the illustration shows her trip distances for each section of the race. So what we're looking for is what is the rider's average speed during the 90-minute bike race. So average speed, that's going to be her total distance, divided by the her total time it took her to do so. Now, so we're going to add up her things. So we've got 4 plus 3 is 7, plus 3 is 10, plus 2 more is 12. So her total distance, that's going to be average speed. Her total distance is going to be 12 kilometers. And this particular one, being that they're giving it from 0 kilometers per hour to 30 kilometers per hour, we're going to want to keep with that same per hour type frame. So right now we have 90 minutes. So 90 minutes is 1.5 hours, right? 1.5 hours. So how do we make half an hour into a decimal? So that's going to equal 1.5 hours. So we've got our distance and we have our time. So I'm going to come over here to this other side. My total distance is 12 kilometers divided by my total time, 1.5 hours. And that's going to be 8 kilometers per hour. And this is something that makes sense because it is between the 0 kilometers and 30 kilometers because this is her average speed.